Okay, we're back. So I'd like to now talk a little bit about magnetic force. And we've already seen a couple different types of magnetic, or ways that magnetic force can be applied. You guys have seen if I have a north and a south pole here, and then it's attracted to, this is the north side. Don't know if you can see that. It is attracted to the north side. Like poles do not. Okay, so two magnets can be attracted to each other. Actually, I'm going to take the horseshoe magnet now, and we're going to do something kind of cool with it. Okay, you can see I've got the horseshoe magnet suspended on just a copper, and copper is not magnetic. It's suspended on a copper pipe, and what I'm going to do, it's going to take me a little bit to get it set up. What I'm going to do is tape a paper clip to the chair, or excuse me, the paper clip is on a string. Okay, I'm going to tape that string to the chair, and then I'm going to levitate the paper clip, which always is kind of fun to do, even if it's not particularly, scientifically noteworthy. Okay, that's a little too long. Still a little bit too long. Let's do this. Let's pull this down just a little bit. I'm sorry, my video skills are not good with this sort of stuff. Okay, let's try this now. Aha! Look at that. Okay, so I've got the paperclip tied to a string. String is taped to the chair. Okay, and that string, that magnet, that big horseshoe magnet, creates such a strong magnetic field that it takes something that's not normally a magnet, the paperclip, and it holds it right up. There's nothing else happening here. I can put my finger right through this. If I move this down a little bit, paperclip falls away. And then if I put it back up, it goes right back up. You can see that it even kind of jumps back and forth between the two sides, and it even kind of makes this thing wiggle a little bit. Okay, so magnets can also attract things that aren't normally magnets, such as this paperclip. This paperclip is being magnetized right now. There is actually another way that the magnetic field can act, and that's what we're going to talk about now. Magnetic field can do something kind of neat to just, not even things that are metal, but just regular old electric charges. An electric charge will actually experience a magnetic force if it does this kind of weird thing. If it moves perpendicular to a magnetic field. Okay? So, if I were to have an electron moving like this, okay, say it's moving this way, and it's inside this big magnetic field that is aligned this way, is the charge moving perpendicular to the field? No. So there would be no magnetic force. On the other hand, if I have a charge, let's say a negative, but it could be a positive, moving up this way, and I have a field like this, then there is a magnetic force. And the way that magnetic force acts on it, the effect of the magnetic force, is really interesting. So that's just a fact you have to know. If a charge is moving perpendicular to a magnetic field, then it will experience a magnetic force. Okay? There doesn't even have to be a magnet. I mean, a magnet creates a magnetic field. You don't even necessarily have to have a magnet particularly close. If there's a magnetic field present and an electric charge moves through that perpendicularly, it cuts across the field lines, it will experience a magnetic force. And that effect, like I said, is very interesting. If an electric charge moves perpendicularly through a magnetic field, it will actually start to move in circles that are perpendicular to the field. Now this sounds really weird, so I'm going to draw you a picture for it. Let's pretend that we have a magnetic field pointing out of the page. And this is how I'm going to draw it. Okay, so you can pretend that these are just kind of like vectors that are pointing directly out of the field towards us. Okay, imagine you're looking right at the tips of the vectors. And if I were to take an electron and shoot it into the magnetic field this way, as it goes into the magnetic field, if those vectors are coming out of the paper at us, our electron is moving perpendicularly to those field lines. So what it will do is actually start to move in a circular fashion. Okay? Why does it do that? That's just the way the magnetic force works. Okay? Electron starts moving in circles. This is really weird, but it is what happens. Matter of fact, one of my favorite experiments that I ever did when I was in college was an experiment in which electrons were emitted from a light, and we put them inside a magnetic field, and you could literally see, because there was a gas inside the field, so the electrons would interact with the gas and cause light to be emitted, and you could actually see the path that the electrons were taking as they curved or as they moved in circles through this gas. It was really, really interesting. Okay, so magnetic forces don't even necessarily have to involve two metal objects. Even if you have an electric charge moving through a magnetic field, that still works. Now I want to talk about the kind of the trickiest conceptual topic in magnetism. That's electromagnetic induction. We talked at the beginning about how similar electric and magnetic fields are, okay, and that they're really two different types of the same overall phenomenon, just kind of like expressed different ways. There's an interesting property with them, and this shows us that they're related. Changing the strength, or the size, the magnitude, of one of the fields creates the other type of field. So here's what this really means. If you have an electric field and you vary the size of that electric field, and a magnetic field will automatically be induced. It will be created with you doing nothing other than changing the size of the electric field. Now you could change the size of the electric field in a number of ways. You could move some electric charges closer to or farther away from a point. You could put more electric charges at a certain point. You could change the configuration of those charges. The idea is, though, is that if you change the size of an electric field at a certain point, if the electric field gets stronger or weaker, what you do is you create a magnetic field that is associated with that, okay? So this means that whenever an electric charge or magnet moves, it not only changes the strength of its own field, because, if a charge gets closer to you, the field gets stronger because you're closer to it, it also creates the other type of field. And if you create something from scratch, if something goes from 0 to some value, then isn't that field's value changing? So let's say you move a charge from one point to another. Okay, the electric field gets stronger. Okay, you've created a magnetic field. But the fact that you created that magnetic field means that the magnetic field you created has its size changing. And therefore, if the magnetic field's size is changing, that creates another electric field. And since that electric field's size is changing, it creates another magnetic field. And you go down this rabbit hole. They're not all the same size field. They get weaker and weaker as you go. But you go down this rabbit hole of electric and magnetic fields being created because the other one is changing. And it is just a very, very interesting phenomenon. We have lots and lots of applications in motors and other technologies that use this. Okay? Long story short, if you move a charge, it creates a magnetic field. And if you move a magnet relative to a conductor, that creates an electric field. And this whole idea is known as electromagnetic induction. Or, in short, Lenz's law, after the guy who first described it. Lenz's law. Okay? Now, there are a few examples of this that I'm going to share with you. I might get to all the examples, or I might have to do one more short video. A current-carrying wire is our first example. So let's say we have a wire like this. Okay? And the current's flowing, let's say, this way through the wire. Just the fact that current is flowing through that wire means that charges are moving through it, right? And charges, electric charges, if they move, they induce a magnetic field by doing nothing other than moving. So, current in a wire means charges are moving, which means a magnetic field is created anytime there's a current in a wire, okay? So let's say the current's flowing up. You guys don't need to know the direction or the size of the magnetic field. You just need to know that it happens. You can learn that stuff in other physics courses. If you have this, what happens is you actually get it's kind of weird, a magnetic field that I shouldn't have drawn it there. It kind of encircles the wire, okay? So imagine these dotted circles are going out. They're not going up the wire, they're kind of spreading out from it radially, okay? So we can actually see that there is magnetic effects from current in a wire by looking at our magnets that were magnetized poorly. So remember, on the compass, the south pole of the compass points towards Earth's north pole. So if this magnet is properly magnetized, then the north pole should attract the south pole of the compass. The compass should stay exactly as it is as I bring the north pole close. We see that that doesn't happen. Okay, this is wrongly magnetized. Right now, this is the south pole of the magnet. This is the north pole of the magnet. We don't want that. Same thing for this one. Okay, so there is a way to remagnetize these. Let me show you. There's this neat little thing that I have in my room. You can see the cord off to the left-hand side of the screen. And it is, I don't know what the actual name is because I don't pay attention to these things, and I should, is a remagnetizer. So it's plugged in, and you see these green things. These are essentially solenoids. A solenoid is just a loop of coil, okay? What I'm going to do is I'm going to put the same magnets that I just used, okay? I swear I'm not swapping out new ones. What was this? Okay, yeah, north and south. I'm going to connect them. So I put them inside this solenoid, okay? Now in a second, I'm going to flip the switch, and current is going to run through these magnets, or these wires. And since current is running through them, that's going to generate a magnetic field. Remember how I said these magnets are really cheap? Okay? It's really easy to change their magnetism, to change the polarity of them. Okay? So what's happened is these have become demagnetized or wrongly magnetized. I want to make it right again. I want to make it so that the label is actually what they are. So current is going to run through these solenoids, a really high current actually. And when it does that, it's going to cause a magnetic field so strong that it takes all of the atoms in these magnets and it realigns them. Okay, it's going to remagnetize them correctly. So it's going to be loud. I'm going to flip the switch. It's going to run for about 3 seconds, then we'll test it. Okay, so let's see if it worked. Because sometimes I do it the wrong way. Okay. By the way, because so much current runs through these actually get really hot afterwards. If I do this a lot really quick, it starts to smoke a little bit. So that's kind of fun. All right, we said that the magnet, or the compass, same compass we were using before, should now point towards the south pole of the compass, which points north, should point towards the north pole of my magnet. Here's my magnet, compass. Oh no, it's still wrong. Okay, I must have had it flipped the wrong way. So let's do this then. Ugh, come on. Sometimes I have it set up the wrong way. South, north. Okay, let's try it now. Okay, so now I have the north pole of the magnet, and it is attracting the south pole of the compass, just like we wanted it to. And the other one should be the same way. Yep, north pole attracts the compass, okay? And we still see that south and north attract, okay? So, I guess I'll show you the next two in just a little bit, but that was one way that you can see that this thing that has a bunch of current going through these solenoids, this remagnetizer as I call it, the current going through those solenoids creates a magnetic field so strong that it can remagnetize these magnets, even if I mess it up the first time. Okay? So that's one example of electromagnetic induction. A really, really strong electric field, changing electric field, because you have charges moving, creating a magnetic field that is strong enough to remagnetize the magnets. I'll be back in a little bit.